Hi guys, Harry here. Welcome to Scrap Science. So you'll probably remember a couple of months ago we crystallized some potassium chloride out of diet salt, and today we're going to get around to actually using this potassium chloride. We're going to build ourselves a chlorate cell. Now what a chlorate cell does, or is meant to do, it's meant to convert potassium chloride into potassium chlorate by electrolysis of potassium chloride solution. I don't particularly need any chlorates for anything right now, but I just thought it's a pretty interesting synthesis that I wanted to cover. So now first things first, we need to make up our solution of potassium chloride. We're only going to be making a really small chlorate cell, at least for now, so we're just going to be using this little 50ml beaker. And what we need to do is, if we're going to use 50 milliliters of water, we're going to need approximately 12.7 grams of potassium chloride in order to have a saturated solution of the salt at around room temperature. So what I'm going to do is measure out that mass of potassium chloride. It's hard to see on camera because it's so white, but there we are. That's about 12.7 grams of our potassium chloride. So all we need to do is add 50 milliliters of distilled water to that, and then maybe we'll heat it up on the hot plate just to make sure that all dissolves quickly. And there, we've got that done. Hopefully there's not too much potassium chloride that precipitates out after we're finished there. Maybe we'll have to filter this later. Anyway, we'll go ahead and put this in this styrofoam box that we're going to do the rest of the experiment in, just to let it cool down. So now that our solution's pretty much ready, we'll go over all the stuff we're going to need for the actual electrolysis. First thing is a power supply, because we're going to be pumping electric current through the solution, so we're going to need something to power that. What I've got here is a computer power supply, and I've connected up a voltage and current controlled power supply up to the 12 volt line on this thing, just so that we can get some really fine control over how much current and how much voltage we're actually putting into the cell. It's pretty much essential that you have a current controlled power supply, at least for chlorate production, just because it makes it a lot easier to tell how quickly you're actually making chlorates. So basically this just stays on the 12 volt line from the PC power supply, and then on the outputs here we can output any voltage we want, and this is what will actually be connected up to the cell ultimately. Currently I've set the voltage and current limits from this power supply to 5 volts and about an amp respectively, but we'll fine tune that in a little bit. The next thing we need are our electrodes, and these are the metallic surfaces that will actually be doing the chemical reactions within the cell. First one I've got here is the negative electrode. This will be our cathode. Now the cathode is the electrode that you really don't need to worry about in a cell like this. It's doing a really easy reaction. It's just reducing water into hydrogen gas and hydroxide ions by the equation on the screen right now. And because it's the cathode, reduction is occurring, and you don't actually have to worry about your metal oxidizing or corroding really all that much. I've chosen just nickel foil to use as my cathode in this case, just because it's very corrosion resistant, just for any like mist of chlorate solution that kind of gets onto the outside of the electrode. It's really not a big deal though. You can use pretty much any metal for your cathode if you're making one of these cells, although maybe steer clear of aluminium, zinc, stuff like that. Just stick with maybe iron, nickel, stainless steel, or even just regular steel. They'll all work. Titanium's actually the best, so if you can get that, use that as the cathode. I've heard that's the most efficient. Sadly I don't have any, so I'm stuck with using this nickel foil. Now the anode, this electrode is a little bit trickier because its job is to oxidize the chloride ions to chlorate ions by the reaction that's on the screen right now. Now because it's the anode in this electrolytic cell, it's going to undergo oxidation So pretty much any metal that you use for this, like any common metal like iron, copper, stuff like that, will pretty much inevitably corrode and oxidize in preference to the actual reaction that we want to happen, the chloride conversion to chlorate. And there are actually very few choices that you can actually use successfully in a chlorate cell like this. Some of the only ones that I know of are, for starters, carbon electrodes. Something like this work pretty well. They do tend to fall apart and leave your solution with a whole bunch of carbon dust in them. So they're a cheap option, but they work. I think all of the platinum group metals would work as well. I know platinum certainly does, so if you've got a platinum electrode, then this would be nice and easy. Don't use gold if you're planning on doing that. Gold, as unreactive as it is, will actually dissolve and corrode away under the conditions of a chlorate cell, so don't use a gold electrode. Basically, aside from some obscure anodes that you could use, I guess, if you've got one, you're basically stuck with using graphite, carbon electrodes, a platinum electrode, or what I've got here is a mixed metal oxide anode. And what this is a bit of titanium mesh coated with a thin coating of iridium dioxide and ruthenium dioxide. Basically, this is an ideal anode for a chlorate cell. It's pretty much specifically designed for generating chlorates from chlorides. It doesn't degrade at all and just leaves you with an excellent... It just leaves you with a really nice, clean solution of chlorates. I bought this off eBay, and what I've just done to make a good connection is got some of that nickel foil and just kind of crimped it around the top, and this will work to dip in to our beaker and act as our anode. So what we can do with our electrodes, I've set them up in such a way, we've got this beaker, I've transferred the solution into another beaker just for now to show you this. I've bent the cathode in such a way that it'll just clamp on nicely to the edge of the beaker. You can see the electrode just kind of sits on the edge of the glass there, and then with our anode we can just sit that in there and connect up our power leads to these bits of nickel on the side, and then hopefully that will work nicely as a chlorate cell. Now before we get started, one of the main drawbacks to using an MMO anode like this, well, actually all anodes do this to some extent, but MMO especially, is that we can't let the chloride concentration drop below 10% by weight, around about, or we'll suffer some pretty harsh degradation of the anode. So what that means is we can't just leave the cell running for however long we want and just expect to get however much chlorate out of the cell. We have to make sure that we run it for short enough time to not let the chloride concentration get too low, because they will lower over time as they get converted to chlorates. And there's only so much chloride that we can fit into the 50 milliliters that we've got there. I'd like to get through, I've got a whole 19 grams of potassium chloride. We only could fit about 12.7 grams in there. So what we're going to have to do, I'm going to leave this cell running for 3 days when we have it. And what I'm going to have to do is every day, every 24 hours, add a little bit more chlorate to the cell. So how I'm going to run my cell, I've done quite a bit of calculation over here. I'm going to run the cell at 1.03 amps, which should, at the 55% efficiency that the cell runs at, or how my cell should run at, given some side reactions will happen, maybe we'll generate oxygen gas, chlorine as well. What will happen is every 24 hours we will reduce the chloride concentration to about 10 to 15%, which is getting close to the limit of what our anode can handle. What it's going to do is that every 24 hours it's going to convert about 6.31 grams of our potassium chloride into potassium chlorate, and so every 24 hours I'll add an extra 6.31 or thereabouts grams of potassium chloride to just saturate the cell. So with that in mind, I'll leave the cell running for about 3 days, and hopefully by then I'll have worked my way through about 25 grams of potassium chloride, which is about all I have. All that's basically left to do now is filter the solution, and then we should be just about good to go. I've connected up all the electronics. I've connected up this fan on the side of the box to 12 volts as well, just because at the start we're going to generate just a little bit of chlorine gas, which we want to just make sure that goes away. So like if we turn the power supply on, you can see that fan running, and it's blowing out the edge there, and it should also keep the lid closed, keep everything protected from the outside elements when we have the actual cell running. And so now all we've got to do, by the way, I've got this lead acid battery in here just to weigh down the box. So if we dip in our electrodes, have this one onto the side here, and just dip in our MMO there, and now if we turn on the power supply, we should see some gas bubbles start forming on the electrodes. No, maybe yeah, look at that, zero current means I've got something not connected properly through my wires. Oh, yep, there we go, that's a little bit better. So what that should be doing right now is generating chlorine on the anode and hydrogen gas on the cathode. That's working very nicely. It's not like frothing up or anything, all the bubbles are just popping straight away. Excellent. I might reduce the current just a little bit to begin with, so I'll go ahead and do that now. I've now reduced the current to a bit over 0.5 amp, and it's looking a little bit nicer down in the cell. It's a little bit tricky to see the hydrogen coming off the cathode from this angle, but oh well. Anyway, for the first little while, what's going to be happening is we're just going to be generating hydrogen gas on the cathode. In fact, we'll be doing that for the whole time. And on the anode right now, we're just generating chlorine gas, and that's because the cell hasn't had time to become basic, or the pH hasn't risen yet. It's not until the hydroxide ions generated on the cathode actually start increasing in number to the point where it becomes a pH of around 9 or 10 that the reaction on the anode actually becomes the one on the screen, chloride to hypochlorite ions. Once that starts happening, we can get hypochlorite ions oxidized to chlorate ions, and then it works really well from there. What I'm going to do now is just close this up, leave it running at this low current for about an hour. It's 4:30 now, so by 5:30 I'll set the current to the actual current that we want, 1.03 amps, and then from there what I'll do is just do that thing that I was talking about before, wait 24 hours and then add the 6.31 grams of potassium chloride to the cell just to bring the chloride concentration back up, and we should be good to go just like this for the next 3 days. You can see even after just 10 minutes or so that gas production on the anode has slowed down considerably because now it's favouring the reaction that the chloride ions to hypochlorite instead of actually generating that chlorine gas as we saw before. And now that the cell's been running for about an hour, so we're at 5:30 now, we can go ahead and turn up the current to the 1.03 amps. If I can actually get in there, that we wanted to begin with. Yeah, that's close enough. Now you can see the cell is running a whole lot faster. All that hydrogen gas forming on the cathode is making the solution quite cloudy, but hopefully all the bubbles rising to the surface don't create a whole bunch of mist that gradually just chucks all the water out of our container. But by the way, I'll leave that going for the next 24 hours and I'll come back and add our 6.31 grams of potassium chloride to it. Continue doing that for the next couple of days. It's now 8:30 the next day. We've had the cell running for about 16 hours, and you can see that the electrodes are holding up fairly well. Obviously the chlorine coming off the cell isn't all that good for the nickel foil that I'm using. Getting a little bit of rusting on the edges there, but hopefully that won't be too bad over the next few days. It's now 5 o'clock on Sunday, and we've got two things to do. First of all, we've got to grab another 6.31 grams of potassium chloride and add it to the cell. And then the second thing I've got to do is, you can see the nickel has really started to corrode a lot. It's probably due to all the chlorine coming off the cell and all of the oxidizing solution that's spraying onto it. So what I'm going to do is kind of try to clean off that electrode. You can see some of that oxide has gone in and entered the solution down there, which doesn't make it look too nice, but we should be able to recrystallize the chlorate later and fix all that up. So what I'm going to do is just turn off the cell for a little bit, clean off the electrodes, and see if we can kind of maybe protect them a bit. So I've weighed out about 6.3 grams of our potassium chloride. I've wrapped some electrical tape around the top of our electrodes just to protect them from oxidizing, and I've tried to clean off the cell a little bit. It's a little bit disappointing that our solution is a bit grey now and has a bunch of nickel oxide, but we'll just have to put up with that. So all we're going to do now is just add our extra potassium chloride into the cell. And one more thing to mention about the cell, which I didn't mention before. If you know anything about chlorate cells yourself, you'll probably wonder why I haven't added any sodium dichromate to the solution, because that does increase the efficiency of this process substantially, because it hinders any reduction of chlorate back into chlorides, which is the reverse of what we're doing, which is a reaction that happens on the cathode to some extent. And I've simply not done that because A, I don't have any dichromate. B, I don't really want to work with dichromate. It's pretty carcinogenic and nasty stuff. And 3, I really don't care about efficiency. I'm making like 30 grams of chlorate with this chlorate cell, so it really doesn't matter if we use like a bit more electricity than we would otherwise doing it this way. It's the same thing with the amount of surface area on the cathode. If I used a small surface area, it would increase the efficiency of the process. However, once again, I don't care about efficiency, and I'd like to have a high surface area on the cathode just to make sure that we're always getting a little bit over an amp of current. Anyway, we've had it running for a little bit over 24 hours now. So all that's left to do is wait another 24 hours, do our last addition of potassium chloride, and then another 24 hours after that, the cell will be done and we'll extract all of the chlorate that we've produced. It's now another 24 hours later, and it's time for the final addition of our chloride. Really, this is a pretty short chlorate cell run time, only 3 days. We're not actually generating all that much chlorate, about 30 grams in total, but that's all I want really. So here I have the final addition of the potassium chloride, and I'm going to add it into the cell. One other thing I'm sure you've noticed is how black the cell has gotten. It's obviously just such a corrosive environment that all of the nickel is converting into oxides, like falling into the cell, and it's just incredibly black now, which shouldn't happen, but it has for ours. Obviously, if I try this again, I won't use nickel metal to connect up our stuff. I thought nickel was pretty inert, but obviously it's not inert enough for this application. Maybe I'll get some titanium or something if I do this again. But all that's left to do now is wait another 24 hours and the cell should be pretty much done. Well, it's done and it looks absolutely disgusting. You can't even see what's going on in there. But, you know, our current and voltage have stayed pretty constant, which means our electrodes are fine. But what I'm going to do now is cut the power, take the electrodes out, see if I can clean them off, and then I guess we will try to extract the chlorates from the solution. One thing to note, for an MMO anode, or any anode really, you shouldn't leave the electrodes in the solution while the cell isn't running. Alright, you need power flowing through those electrodes to keep them good. Well, as bad as it looked, the electrodes seem pretty fine. That's the cathode there, and then the anode, like really the nickel that we used to connect it up, doesn't actually look all that touched by the oxidizing conditions. Maybe a little bit there, but I don't know, obviously there's actually not all that much contamination in there. Just a tiny little bit makes it look absolutely terrible. So hopefully it will actually be easy to remove in the end. And there we are. I've cleaned up the edges of the beaker a little bit so we can kind of see it a little bit better, and we can see right down the bottom. You can't really see on camera, but there is quite a bit of salt in the bottom, something that's not dissolving. In fact, there's quite a lot. So that's very promising. Hopefully that's pretty much all chlorate, which we should be able to extract by filtration. Anyway, I don't have time to extract that now, so I'm just going to leave that in there to do its thing for the rest of the week, and then on the weekend I will go ahead and filter out all of the chlorates. Now, it's actually been a couple of weeks since my last scene. I've been away for a while, and I've just left this solution in the beaker over those 2 weeks. You can see that all of the particles of nickel oxide that were in the beaker have kind of settled down to the bottom, which is a good sign that we'll be able to filter them off later. The first thing we need to do with this to extract all the chlorates that are in here is dissolve all the chlorates back into the water so that we can filter out the nickel particles. So to do that, we're going to raise the temperature, make it boiling, so that hopefully all of the potassium chlorate will dissolve. This boiling will also help us in the fact that it will convert any hypochlorites that are still present in the solution and convert them to chlorates, which is exactly what we want. I'm also going to add just a little bit of water to the solution, just so it makes it a little bit easier for us to dissolve all of the chlorates in there. So it's been a couple of minutes, we're nearly at boiling temperature, and we have dissolved all of the chlorates. We're going to leave it at this temperature for a few more minutes just to make sure that we convert any present hypochlorites into chlorates. And after 3 filtrations, we have ourselves a pretty crystal clear solution of our potassium chlorate. Nice. Anyway, if we now just go ahead and let this cool down, you can already see we're starting to form some little crystals of what is hopefully our potassium chlorate. If we leave this over the next hour or so to cool down to room temperature, hopefully we'll have a whole bunch of potassium chlorate crystals, which will be nice and clean, and we'll be able to just filter those out, and they should be pure enough for anything we use them for. And there we go. After cooling in the freezer for a little while, this is what we're left with, a whole bunch of crystals in the bottom of the beaker. They do look suspiciously like the potassium chloride that we started with, but hopefully they are actually potassium chlorate instead. That is our initial recovery of the potassium chlorate. It's probably quite heavily contaminated with potassium chloride, so I should probably recrystallize it, but I'm not going to because I don't care enough to do that yet. And just to dry it all out, what I'm going to do is stick this watch glass over the top of a beaker full of boiling water, and hopefully that'll just heat it up enough to evaporate off all the water and dry it all out, and then we'll be able to store it. So now, while that's going ahead, just to prove that we have made chlorates and it's not just potassium chloride from the start, what I've done is I've soaked a small piece of paper towel in the what should be a chlorate solution up there, and I've let that dry out over the last 10 minutes or so. So this is pretty dry and should be soaked in, well, pretty strong oxidizer. So if we burn this with some matches, we should see it act slightly differently to just regular burning paper towel. So you could see from how quickly it burnt the paper and how crackly it sounded. Hopefully you picked that up on the camera. We do have a strong oxidizer impregnated into the paper, which should be potassium chlorate as we expected. Anyway, the chlorate is nearly dry, so I'll get the scale ready to measure it all out at the end to determine our yield. And there we go, our final yield is just about, well, exactly 7.5 grams, which isn't all that great considering we expected to get around about 20 grams of potassium chlorate. I don't really know where it all went. I mean, the only place it could be is in there, and I can tell you there's not much chlorate left in there because this is, you know, it's not very soluble and it's pretty cold, so it would have all crystallized out. So, you know, we didn't get all that good a yield. Well, anyway, at least it worked. We did get 7.5 grams of potassium chlorate out of our chlorate cell. Our electrodes did fine. Everything worked out quite nicely. Overall, I think we can call this a successful project. So, see you later.